Okay, so the talk today is functional programming, for fun and profit. And the title is actually a bit misleading because as I rehearsed this morning, I realized it's not as fun as I thought it would be. But since you're already here, you might as well just stay till the end. I want to open up by this GitHub README article titled "Functional Programming is Finally Going Mainstream." And this is one of the many articles that talks about the increasing number of adoption of functional programming over the years. Along with it, you probably have seen discussions, tutorials, or just explanations about functional programming concepts here and there. And you probably have seen memes and parodies on some of the concepts in functional programming, like this one on monads. Oops. And you also might be wondering, what is functional programming really? And should I care about it if I just want to write my Ruby code? After all, rumor has it that in Ruby, everything is an object. So this is what I want to convince you today. Functional programming helps us write better Ruby code. So before going to that, a bit about me. My name is Shih, and I go by Jenny to make everyone's tongue less busy. Two big events happened to me 2 months ago. I started working at Shopify and also moved from Taiwan to Toronto in Canada. I primarily program with Ruby, but there was a period when I almost ran away with Elixir, and that's the main reason that this talk is happening. You'll soon find out that I drew a lot of inspiration for this talk from Elixir. And if you click into my personal website, you'll see a string of chicks that follow the cursor wherever it goes, and it's really therapeutic. Okay, with that, let's talk about the functional programming paradigms. According to Wikipedia, it is a way to classify programming languages based on their features. So there are tons of programming paradigms out there. Object-oriented programming is one paradigm characterized by message passing between objects and encapsulation of the state and behavior. Functional programming, that is the focus today, is another programming paradigm that has its own set of features, which I will talk about in detail shortly. To help us put things together, let's first look at a mental model. So this is there are 3 elements here that constitute a program: value, behavior, and time. To see what I mean, we can look at an example. So here we have a function puts that prints out the string hello world and return nil. We see 2 things: behavior and value. Behavior is the verb, the decisions, and value is something that holds data. Another example, this time we assign RubyConf Mini to this variable conf, and later changing it by upcasing it. And we see time. So somewhere between line 2 and 3, some bytes in some machine switched in, and in this case, it's my machine. And the value of this variable conf is no longer the same. To understand more of what time is, because I understand maybe it's a bit of a vague, more abstract than the other 2, we can think about state, which, if we're breaking down, is the value of an identity that we hold on to in a given period of time. And this is my mental model of what an OO program looks like. An object encapsulates the value and behavior together. And the time is implicitly inside both the value and behavior, because a value can be changed over time, like we just saw. And so this method. And a program would be composed of many objects that interact with each other. So that's object-oriented. As for functional programming, for each element, there's a distinct concept associated with it. And our agenda today is to talk about each element and look at them one by one. So first of all, the value. To talk about value in functional programming, we need to talk about immutability. The concept of immutability is this. You don't change a value once you initialize it. And for Ruby, it would be like you freeze an object, like you freeze this array. And for objects defined by the class keyword, it would be like saying goodbye to the attribute writer and attribute accessor, because these two keywords are giving power to other objects to mutate the attributes of this object. And that goes against the definition of immutability. So why does that matter? With immutable objects, we don't have shared states anymore. We don't have to care about when and where the object is changed, because it's never changed. So the example is this. We have this flight struct, and suppose today I initiate my flight to have the date of, to have the date of November 14th. And my friend is sharing the flight with me, so they just copy my flight. But then they later on change it to another date, which is November 13th. And now when I look at the date of my flight, it's also changed. And of course, that was a code that I made up solely for the purpose of this demonstrating. But in real world, it happens. It may happen through a shared variable that you forgot to reset after each test, or it may be the hours that you spend debugging to figure out why a value has changed to nil. And chances are you've experienced similar situations. With immutable objects, we are eliminating the possibility of mutating shared state. We don't have to care about the object state at any given time. And that's a huge benefit. Okay, so next is how we can do that in Ruby. And the first advice sounds weak, but I think it's important. It's to think twice about every mutation of the state that you make. And at the language level, Ruby doesn't have a language-wise guardrail for immutability, like some other programming languages have. So it largely comes down to ourselves to not write mutable code. And this is a good habit to have, whatever the code that you're writing, because as we just saw, we are just less likely to produce bugs if we have immutable objects. And there are actually tools that we can use. First of all, this is a gem called Dry Struct that's part of the Dry Ruby collection. Dry Ruby is a set of powerful and wonderful gems that support a lot of functional programming ideas, including this one, which provides a data structure that is like a struct in Ruby, but immutable. And but sadly, I've never used the Dry Ruby in production setting, and I would really love to hear more about it if you have used it or you contributed to it. Come talk to me if you are. And the next thing that I feel quite excited about is the data define that will come out in Ruby 3.2. You can already play with it in the latest preview. And this is a PR that created the data class by Victor Shepelev. As the title says, it is a simple immutable value object. And Brendan Weaver here has written a really nice blog post about it, and I highly recommend you to check it out, along with the PR, to know more about it. And just to emphasize again, although we have those nice tools to help us, the equally important is to be mindful about the state, the mutation of the state, and the possible consequences of it. So that concludes the value part of functional programming. We know by having the constraint of immutability, we have a program that's easier to debug and reason about. Next is behavior. And how functional programming think about behavior is largely by pure functions. A pure function is a function that satisfies two conditions. First, it only depends on the input argument. It does not depend on any other value outside of the function scope. So this is not a pure function because it is invoking time class in the method, which means it depends on this time module, and we get different results every time, even though our input stays the same. And in our case, the input is nothing. If we tweak it a bit by passing the timestamp as an input instead, then we have a pure function. Because now we can be sure, as long as this timestamp is the same, then our output is the same. So the second condition for a function to be pure is it's to not mutate states. And it is equivalent to saying it has no side effects. This is not a pure function. It satisfies the first condition that it only depends on the input argument, but it changes the string. So any variable that goes through this function will be changed forever. And to make it pure, we don't update the variable itself, but to create a new string and return that new string, so that the original value will not be affected. And the question again, why? Why do we want to limit ourselves like that? And I'm just going to quote Joe Armstrong, the creator of Erlang here. The problem with OO languages is they've got all this implicit environment that they carry around with them. You wanted a banana, but what you got was a gorilla holding a banana in an entire jungle. And I will highlight the implicit environment here. No implicit environment is a big deal, because let's think of this orange circle as what loads into our brain. And we see the problem with implicit environment is that although we only care about the banana, we need to load a lot of things into our head all at once. And that can be overwhelming and distracting from our purpose. And if we don't have implicit environment, we are able to shrink our focus to one small chunk of a problem at a time. And that brings a lot of advantages. First of all, it means that you will be more efficient because you can focus better. And you're likely to produce bugs because now you have the brain space to attend to details that you wouldn't likely to gloss over before. And the unit tests will be super easy because you have no environment to set up. And it will give your reviewers an easier job because now your PR is so small and neat. And one thing leads to another. If we fast forward a few steps, we're making the world a better place. Now that we know that we want Nobel Prize, pure functions, the next step is how. The first technique is called parameterization, or its equivalent in OO terminology, dependency injection. Some of us might already be familiar with this concept. Here we have a function that subscribes to an email, to a newsletter. We first checked for some conditions. And if any of the conditions is not met, return with the false value. And once we pass the conditions, we add the email to the mailing list and return true. So this is not pure because we have two implicit dependencies: the email form validator and the mailing list instance variable. To fix it, we can put the two objects into the parameter instead. This looks like a simple change, but it is to turn the implicit dependency that we saw just now and make it explicit and predictable. What's my tone? So that's good, but it is still not pure. We see that the mailing list is still mutated. We are still implicitly talking to the environment. So that brings us to the second tip on how to make our functions pure: transformation instead of mutation. So instead of relying on mutating the list to make a change, we can create a new mailing list and return that instead. So it looks like this. Now, let's run this against our two conditions again. First of all, we apply parameterization or dependency injection. So now, this method now only depends on the input argument. And the second condition also checks. Instead of mutating our mailing list, we transform it instead. So the original mailing list is not affected. And just a quick note, this is not the whole new idea either. A lot of us are already using service objects, and if implemented well, the concept of a pure function can go really well with a service object. Okay, and that is the behavior element of functional programming. We use pure function to avoid implicit environment. The next thing we'll look at is time. And to talk about time is to talk about processes and concurrency. Going back to the earlier slide, concurrency in object-oriented programming is tricky because the time element is implicit inside each element. And this implicit timeline creates the possibility of race condition and deadlocks if we have multiple processes running at the same time. And that's why we have the famous / infamous global interpreter lock in our MI Ruby interpreter. This lock allows us only one thread to execute at any given time. It makes the program safe, but also limits our capability for concurrency. Functional programming eliminates the problem because it models the time in an explicit different element. And it turns out when we have immutable data and pure function, we have a great foundation for concurrency. And let's see an example in Elixir. So Elixir is a functional programming language. It runs on the Erlang VM and the OTP platform, which implements this actor model for concurrency. So in the terminology of Elixir Erlang, a process is an actor. And actors don't have any shared states. They can only get one another's state by message passing or message sending. And the process referred here is not an operating system level thread or process. It's a language-defined unit of execution. So one process in Elixir is actually more lightweight than one operating system level thread. In fact, it is so lightweight that millions of Elixir processes can run in one thread at the same time. And there's also this role of a scheduler to decide which process run at which time, but all processes run concurrently. And so let's Elixir. One reason that it can do such thing is its guarantee of immutability at the language level. And some of you might already know, Ruby has introduced a similar abstraction starting from Ruby 3.0. It's called rector. And we can draw a graph that's similar to Elixir's model that represents the rectors. Just like the process in Elixir, we can think of one rector as one unit of execution. And one difference between an Elixir actor and our Ruby rector is that rector contains one or more operating system level thread. And when we enable rector, the global interpreter lock will be assigned to each rector individually instead of one globally. So different rectors can run in parallel, while the threads inside each rector can still run safely in a sequential manner. A rector also doesn't share context with one another. If we want to send an object from one rector to another, we need to first make sure that object is immutable. And if the object is not immutable, we will need to either copy the object or move the object before sending the object over. So that's rector. And as of the latest preview of Ruby 3.2, you will still get this warning says rector is still experimental. But I'm very looking forward to the development of this. So this is all for concurrency, and that's it. Wow, that goes way faster than I thought. Okay, so this is, I'm just going to read this. We are defined not so much by what we can do, but what we don't do. And this is a message we want to send. But what does that mean? So decades ago, a lot of people shifted from the procedural programming paradigm to OO because we realized that as convenient as it is, GoTo is probably not a good idea, and neither does global states. So we stopped doing that and start to encapsulate our states and behavior into objects instead and make them send messages to each other. It's less convenient, but it turns out to be better. And functional programming is getting more adoption now because it has a different set of nodes that it insists on. And it turns out to have great benefits. With immutable data, we avoid the risk that come with shared state. With pure function, we avoid the implicit environments. And together, they provide a great foundation for concurrency. And the best thing is we can do that with Ruby. Okay, so that's it. These are the resources that I found really useful. So if you, and I'm going to upload my slides later on, so you can look at them. You don't have to take photos. But yeah, just to quickly go through the ideas of functional programming and the architecture and some Ruby docs. Okay, that's it. Thank you.